Welcome to N3 Electrotechnology. We'll be looking at the questions and answers from the national examination in November 2019. If you haven't done so already, please smash that subscribe button to support this YouTube channel. Now, the first chapter we'll be dealing with in question 1 is DC machines, which is neither a generator nor a motor, and it's just looking at the construction of a machine. Now, question 1.1, the choice of armature windings is determined by the size and function of the machine. State with regard to the nature of voltage and current the application of the following windings. Now, for lap winding, it is used for low voltage and high current applications. For wave winding, it is used for high voltage and low current applications. Question 1.2. The construction of a DC motor is similar to that of a DC generator. Make a neat, fully labeled sketch of a two-pole DC machine. Show only the following labels. Now, it's important to note that in our diagram, we are talking about the construction of a machine, and there are only two field poles, which means there is one pair. Now, the outer frame is also known as the yoke. We have the field pole, the field coils, the pole shoe, and the armature. Question 2.1. When a coil of a wire is rotated inside a magnetic field, magnetic lines of flux are cut and an EMF is induced in the coil. State three factors that will influence the magnitude of this EMF. Now, according to Faraday's first law, an EMF will be generated whenever there is a change in flux. Now, the size of the generated EMF depends on the magnetic flux density, the number of armature conductors, the number of pole pairs, and the rate at which the flux is cut. Question 2.2. Compound wound generators are used to produce a nearly constant output voltage. Draw a neat, fully labeled diagram of a cumulative compound wound generator and clearly show the following: all the currents and their directions, the input and output powers. So here we have a circuit diagram for a compound wound generator, which consists of a series winding and a shunt winding. Now, you'll notice because it's cumulative, it means that current is flowing in the same direction. Therefore, the current through the shunt winding is in the same direction as the current being produced by the armature. The armature current is the same current passing through the series winding, and therefore the armature is producing current which is being supplied to the load. It is mechanical in, and therefore its power inputs at the armature and power out at the voltage supply. Question 2.3. Shunt wound generators produce relatively constant output voltage, provided the load current is below the maximum value. State two uses of these generators. Now, shunt wound generators can be used as battery chargers and used for the excitation of AC machines. Question 3.1, which is all about DC motors. The method for controlling the speed of a shunt wound motor is both easy and economical. State how the speed of this motor can be controlled in the following circumstances. Now, in order to be increased above normal speed, we will place a resistor in series with the shunt field. In order for it to be decreased below normal speed, we will place a resistor in series with the armature. Question 3.2. The self-induced EMF in the armature of a DC motor makes the motor self-regulating. Give another name by which self-induced EMF is known. It is known as back EMF or counter EMF. Question 3.3. A series machine draws 45 amperes from a 250 volt supply. The resistance of the series field and the armature is 0.1 ohms and 0.25 ohms respectively. Determine the machine's constant if it runs at 1000 revs per minute and the useful flux per pole is 25 milliweber. Now, it's important to note that this question is a series machine. Therefore, current remains the same and voltage is divided. The word draw is used, which also indicates that this is a motor, as a motor draws current from the supply. Now, first of all, in order to work out the constant, we'll first have to calculate the generated EMF. Now, to calculate the generated EMF for a series motor, it is the terminal voltage less the volt drop across the armature and less the volt drop across the series winding. If we substitute all the values in, our terminal voltage is 250 volts. Our current through the armature and the series winding is 45 amps. And that gives us a generated EMF of 234,25. However, remember the question asked to calculate the constant. So we use this formula from our formula sheet. Speed is equal to the generated EMF over the constant and the flux per pole. To manipulate this equation to get the constant on its own, it'll be the generated EMF divided by the speed and the flux per pole. The generated EMF is 234,25 volts and the speed is 1000 revs per minute. The flux per pole in Weber is 0,025 and therefore our constant is 9,37. Question 4.1. A manual faceplate starters are used to limit the high starting currents of DC motors by introducing additional resistance in the armature circuit during starting. Make a neat, fully labeled diagram of a faceplate starter for a shunt motor. Now it's important to note that this is a shunt motor, therefore the field winding and the armature are in parallel. We have our resistors connected in series with the armature. We have our position arm, the no volt release coil, and the overload relay. Question 4.2, which is about efficiency of machines. Two identical 200 volts, 18 kilowatt shunt wound generators are tested simultaneously by means of the Hopkinson's back-to-back test. The current drawn from the supply is 12 amperes. Determine the efficiency of each machine. Now, to determine the efficiency using the Hopkinson's method, it is important to note that I2 is taken from the mains. To calculate I1, it is the power divided by the voltage. The power is 18,000 watts and the voltage is 200. Therefore, I1 is 90 amps. To calculate the efficiency, it's square root over I1 divided by I1 plus I2. I1 is 90 amps and I2 is 12 amps, and that gives us an efficiency of 93.93%. Question 5.1, which is all about AC power. A poor power factor will cost an industrial consumer a lot of money and maximum demand charges. State two methods that can be used to improve the power factor of a plant. Now, we as consumers, we want a high power factor. So how do we improve power factor? We can use capacitor banks and use an overexcited synchronous motor or condensers. Question 5.2. An alternating EMF is represented by the following equation. Now, in my equation, we have the instantaneous voltage is equal to the maximum multiplied by sine, and then the angular velocity in radians per second. Now, the first question states, calculate the time taken to reach 250 volts for the first time. So to calculate the time, the instantaneous value is 250 volts. The maximum value is 420 volts. The angular velocity in radians per second is 628,319. Multiply by 57.3 to convert radians to seconds. Now, in order to manipulate this equation, when we take sine across, it'll become sine to the minus 1 and 250 over 420. Once we've got that answer, we will divide by the angular velocity and 57,3. And that gives us a time of 1,014 milliseconds. Now, question 5.2.2, a very similar question. Calculate the time taken to reach its maximum value. So the question is, what is the maximum value? Well, if we look at the equation, we notice that the maximum value is 420 volts. Therefore, the instantaneous value and the maximum value will be the same. Once again, in order to manipulate the equation, we take sine across. It becomes sine to the minus 1. 420 over 420. Once we've got that answer, we'll divide by the angular velocity and 57,3. And we end up with a time of 2,5 milliseconds. Now, 5.2.3, calculate the instantaneous value of the EMF 2 milliseconds after commencement of the cycle. So here, this is a little bit easier. We have to calculate the instantaneous value, and the time that is given is 2 milliseconds. Now, don't forget your 57,3 in order to convert radians to degrees. Therefore, the instantaneous value is 399,455 volts. Question 5.3. State with respect to an alternating waveform what is meant by frequency of the wave. Frequency is the number of cycles completed in 1 second. Question 6. A series circuit consists of a 35 ohm resistor, a 60 millihenry inductor, and a 200 microfarad capacitor. The circuit is connected across a 125 volt 50 hertz supply. Calculate the following. Now, to calculate the total impedance, we'll use our formula from the formula sheet, but first we'll have to calculate the inductive reactance and the capacitive reactance. Our capacitive reactance, don't forget, is 200 microfarad, therefore it's times 10 to the minus 6, or we can divide by a million. Therefore, our capacitive reactance is 15,915, and the inductive reactance is 18,85. Now, of those two, we notice that the inductive reactance is larger, therefore the circuit is mainly inductive. Now, to calculate the total impedance, the resistance is 35 ohms, the capacitive reactance is, the inductive reactance, 18,85, minus the capacitive reactance of 15,915, and that gives us an impedance of 35,123 ohms. Question 6.1.2, calculate the total current flowing in the circuit. Now, because this is a series circuit, the total current is the voltage divided by the impedance. The voltage is 125, and the impedance is 35,1235 ohms. Therefore, the total current is 3,559 amps. Question 6.1.3, calculate the volt drop across each component. Because this is a series circuit, voltage is divided. Now, current remains the same, so therefore the voltage across the resistance is 124,565 volts. The voltage across the inductor is 67,087 volts, and the voltage across the capacitor is 56,641 volts. Now, in the second part of this question, it asks calculate the algebraic sum of the 3 volt drops. Now, algebraic sum means all we do is we add up the voltages together and we get 248,293 volts. However, to calculate the vector sum of the 3 voltage drops, because this is an AC circuit, we need to use our formula to calculate the total voltage. So here we have our 3 volt drops substituted into the formula, and we end up with a total voltage of 125 volts. So it's important to note that for an AC circuit, in order to calculate the total voltage, we will have to use the vector sum of the volt drops. Question 7.1. Unity power factor means that the current and voltage vectors are in phase. Define power factor. Power factor is the ratio of true power to apparent power. Right, here we have an alternator. Once again, we're still on AC power. A 22 kilowatt, 380 volt star connected 3-phase alternator supplies power to a certain load at a power factor of 0.8 lagging. Now, here we notice that the symbol for a star connected alternator, now where we have a star connection, the line current and the phase current are exactly the same. And to calculate the line voltage, it's square root 3 multiplied by the phase voltage. The information provided, we have a power of 22,000 watts. The line voltage is 380 volts, and the power factor is 0.8. Now, to calculate the phase voltage of the alternator, V phase will be equal to VL divided by square root 3. The line voltage which is given is 380 volts divided by square root 3. and that gives us a phase voltage of 219,393 volts. In 7.2.2, the line current drawn by the load if the alternator is working at full load. Now, it's important to note that when we're calculating the line current on the load, it means we're calculating on the secondary side if it was a transformer. However, this is an alternator and it's only connected in star. Now, because we're given power, the formula for power, because it's a three-phase circuit, it is equal to square root 3 multiplied by the line voltage, multiplied by the line current, and multiplied by the power factor. Now, the unknown factor in this equation is the line current. So to calculate the line current, it'll be the power divided by square root 3, the line voltage, and the power factor. The power is 22,000 watts, the line voltage is 380, and the power factor is 0.8. Therefore, the line current is 41,782 amps. Now in 7.2.3, to calculate the phase current, because it's a star connection, IL is equal to I phase, therefore it is equal to 41,782 amps. 8.1. Now we're looking at the section on transformers. Auto transformers are used as motor starters to start large induction motors. State 3 advantages of auto transformers. Auto transformers have high efficiency, they are smaller and cheaper, and the reason for this is because they only have one field coil, therefore less copper wire is used. 8.2. A three-phase distribution transformer has a delta connected primary and a star connected secondary. The transformer is connected to an 11 kilovolt supply. If the secondary phase voltage is 500 volts, calculate the following. Now, before we worry about the questions, we must first draw our symbols, write down the formulas and the information given. Now, we'll notice that delta on the primary, star on the secondary. It's also important to note that for delta, VL is equal to V phase, and for star, IL is equal to I phase. Now, on the primary side, we've got a line voltage of 11,000 volts, and on the secondary side, we have a phase voltage of 500 volts. Now, if you look at the primary side, because VL is equal to V phase, it means that the line voltage and the phase voltage on the primary side will both be 11,000 volts. Therefore, the first question, what is the primary phase voltage? And they are exactly the same. It's 11,000 volts. 8.2.2, to calculate the turns ratio. Now, when calculating the turns ratio for a three-phase transformer, we always use phase values. Therefore, it's V phase 1 over V phase 2. V phase 1 is 11,000 volts. V phase 2 is 500. Therefore, the ratio is 22 on the primary and 1 on the secondary. Calculate the primary line current if the transformer delivers 180 amps per phase to the load. So the question here is asking for the primary side line current if the transformer delivers 180 amps per phase to the load. It means that on the secondary side, which is the load, IL is equal to I phase. Therefore, it will be 180 amps on the secondary side. Right, the problem we face is that we don't have any current on the primary side. So what we need to do is first calculate the phase current for the primary side. I phase 1 will be equal to V phase 2 over V phase 1 multiplied by I phase 2. And that will give us 8,182 amps. Now we can calculate the primary line current. To calculate the primary line current, it will be square root 3 multiplied by the phase current. Therefore, the line current on the primary side is 14,172 amps. To calculate the full load rating of a transformer in kVA, it is, because it's square root 3 multiplied by VL multiplied by IL, because it's a three-phase transformer. So the only question is, will we calculate the primary side or will we calculate the secondary side, as we should get the same rating of the transformer. Let's work with the primary side. So it'll be square root 3 multiplied by the line voltage of 11,000 multiplied by the line current of 14,172, and that gives us a rating of 270 kVA. Right, moving on to measuring instruments. With a moving coil instrument with an internal resistance of 60 ohms, gives a full-scale deflection when 15 milliamps flows through it. Calculate the following. Now, 9.1.1, in order to change this into an ammeter, a shunt resistor to be used with the meter so that it will be able to measure a current of up to 9 amps. So the formula we're going to use to calculate the value of the shunt resistance, it will be the current through the meter multiplied by the resistance of the meter divided by I shunt. Now, the current through the meter is 15 milliamps. The resistance of the meter is 60 ohms. And I shunt is equal to the total current less the current through the meter. Therefore, the value of the shunt resistor is 0.1 ohms. 9.1.2, a series resistor that the meter can be used as a voltmeter to measure a voltage up to 80 volts. So to calculate the value of the series resistor, it's the volt drop across the meter divided by the current through the meter less the resistance of the meter. Therefore, 80 over the current through the meter of 15 milliamps minus the value of the resistance of the meter, which is 60 ohms. Therefore, the value of the series resistor is 5,273.33 ohms. Okay, question 9.2. An ammeter used with a current transformer gives a full-scale deflection when 5 amps flows through it. State 2 safety precautions to be observed when removing the ammeter after a high current measurement. First of all, we'll switch the main supply off and we will short circuit the secondary winding. State the reason why all current transformers are earthed during operation, and this is to direct all harmful energy to ground. 9.3. The 2 wattmeter method has used to measure the power drawn by a balanced 3-phase load. The readings on the 2 wattmeters were 18 kilowatts and minus 4.7 kilowatts. Determine the total power drawn. Now, very simply, all we do is we add up the powers together, 18 plus negative 4.7, and that gives us a total power of 13.3 kilowatts for a 2 wattmeter method. Right, final chapter on electronics, 10.1. State 2 functions of a transistor. It can be used as a switch or amplifier. A truth table shows the output of a circuit for every possible combination of inputs. Determine the possible outputs of a logic gate having 4 inputs. Now, because we're dealing with binary in this chapter, 2 to the power of 4 equals 16. Therefore, there are 16 possible outputs when there are 4 inputs. Draw the IE symbol for a NOT gate. Now, a NOT gate is an inverter. Very simply, the output will be the opposite of the input. Our very last question, subtract this binary number from the following binary number. Now, we have the binary number of 1, 0, 1, 1. Subtract the following binary number of 1, 1, 0. Now, it's important to line everything up neatly so that you get the correct answer. Now, 1 minus 0 will give you 1. 1 minus 1 will give you 0. Now, 0 minus 1 is not possible. Therefore, we'll need to borrow from the neighbor. Now, whenever you borrow from the neighbor, it is worth 2 places. Therefore, those 2 places less 1 will give us 1. Therefore, the final binary answer is 1, 0, 1. Thank you very much for watching this video. Please hit that subscribe button. Please like this video and share it with your friends. Thank you.